Hi, in this video we create a strange new universe out of nothing and add points and curves to our yet empty virtual world. Recall that everything should be defined with numbers because computer can only deal with numbers. So when we need a point, this point should be associated with numbers. We know the solution, which is the application of coordinate system. Generally speaking, a coordinate system is a geometric reference system plus some measuring instructions, and if we follow these measuring instructions, we end up with numbers identifying a given point. The Cartesian coordinate system is very familiar. In this case, the geometric reference system is just a pair of two orthogonal lines with a unit on them, and we measure how much we should walk along these two lines in order to reach the point from the origin of the coordinate system. The so-called polar coordinate system is also useful in many cases. Here, the geometric reference system is just a half line, and we measure two things: the direction in which we should leave the end of the half line called the origin, and the distance that should be traveled in order to reach the point from the origin. The barycentric, also called homogeneous coordinate system, will be very useful to us, both in the definition of free-form curves and also in dealing with geometries where there is no possibility to measure the distance between 2 points. Here, the geometric reference system is the collection of 3 points, and the measurement goes as follows. We put weight x in the first reference point, weight y in the second reference point, and weight z in the third reference point. This establishes a mechanical system, and we consider that point where the center of mass of this mechanical system is located. So with 3 numbers, x, y, and z, we can identify a point with this center of mass analogy. Let us have a few additional definitions for this barycentric arrangement. So, in the general case, we have reference points R1, R2, Rn, where we put masses m1, m2, and so on. And we consider the center of mass of this mechanical system. From physics, we know that the center of mass is that point where if the system is grabbed, it is balanced even if we rotate it. Instead of rotating the mechanical system, we can also rotate the direction of the gravity. So the property of this center of mass is that the torque computed for this center of mass is 0, no matter what direction the gravity field has, which is possible if the other terms are 0, from which we can express the unknown center of mass as a ratio of the weighted sum of the points where the weights are the masses themselves, and we have to divide this weighted sum with the total mass of the system. So we will use this formula to compute the center of mass in practical situations. So when we define a point R with this center of mass analogy, we say that point R is just the combination of points R1, R2, etc. If we use a real physical analogy, where masses cannot be negative, then we talk about convex combination. Note that for our purposes, or for the purpose of the center of mass formula, we can evaluate it for negative masses as well, and we will use negative masses, but it is not physically plausible. The physically plausible case is when all weights are non-negative, and we know it from practice that in this case the center of mass cannot be far from the object. In some sense, it should be inside of the object. More precisely, it is in the convex hull of the given points. Let us see what this convex hull means for a finite number of points. So I just place points on the plane, and the system always automatically computes the convex hull, which is by definition is the minimum convex set that contains all the points. The convex hull is a very useful term even in our everyday life. For example, if we want to protect our belongings with a fence, the fence should be built around the convex hull, because in that case the length of the fence is minimal. If we want to wrap Christmas presents, then the wrapping paper always follows the convex hull of the present. To demonstrate the power of the combination operation, consider that a line is the combination of 2 points, and if we restrict the combination to only convex combination, we obtain a line segment as a convex combination of 2 points. Similarly, a plane is the combination of 3 points, and a triangle is the convex combination of its 3 vertices. After establishing points, let us consider one-dimensional objects called curves. We learned in mathematics that functions are curves, so it would be pretty straightforward to say that a curve is nothing but a function. Such expressions are called explicit equations for curves. As an example, I put here the explicit equation of a line where m is the slope of the line and b determines where this line intersects the y-axis. As functions are very familiar to us, this approach would be really easy to use, but I have a bad news. The problem is that this explicit equation is too restrictive. We cannot use it in many important cases. The serious limitation is that it assumes, as functions usually do, that for a single x in the domain of the function, we have exactly one y value. This is not the case in many practical curves. For example, with this equation we cannot express a vertical line, because in this case for almost all x values there is no y value, but when x is equal to x0 we have infinitely many y values that belong to the same x. We cannot express a full circle with explicit equation because again here we do not have a y value for an x here, but when we are just below the circle for a x value we will have two y values, so again we do not have a function. This is a general curve where it can happen that for a single x we will have more than one y value, which is against the definition of the function. It was a good idea to establish a connection between the x and y Cartesian coordinates with an equation like this. But it was a bad idea to assume that y can be unambiguously expressed from the other coordinate, from coordinate x in this case. So instead of explicit equations, we use implicit equation, which means that we put x and y Cartesian coordinates in algebraic expressions, and to establish an equation, we make this algebraic expression be equal to 0. Instead of working with Cartesian coordinates, we can replace them by position vectors of the identified point. So a curve in 2D can also be expressed as a scalar equation where the variable is the position vectors of points. This implicit equation can handle all the problematic cases discussed so far. We have already seen the implicit equations of the two-dimensional line, which is just a linear expression where a and b are the Cartesian coordinates of the normal vector of the line, and c defines the signed distance from the origin using the units of the normal vector if it is not normalized. The circle is the collection of those points, x, y pairs, where the square distance from the center, denoted by x0, y0, is equal to the square of the radius of the circle. This geometric definition is expressed by the equation of the circle. It has no problem to handle the case when for a single x we will have two y solutions. Also, this vertical line can be represented by the implicit equation of the line, in this vertical line, x is equal to x0. So in the implicit equation, if we select a to be 1, b to be 0, and c to be minus x0, then we obtain x minus x0 equals 0, which means that x is equal to x0. The third option to define curves is the application of the parametric equation, which assumes a curve to be a motion. So we have a clock representing the time, and as time elapses, the motion is at a different point of the curve. So to define a curve for every point of time t, we need to know where we are, so we need two functions in 2D to define the xy Cartesian coordinates, or three functions in 3D, because the third Cartesian coordinates should also be determined. Or instead of using three functions determining the location as a function of time, we can also use a vector equation that immediately provides the position vector as a function of time. The first example is the parametric equation of the line, where x0, y0, z0 is just the position of the motion when the time is 0, and vx, vy, vz are the three components of the velocity. If t can take an arbitrary real value, then this equation generates all points of a line. To get the parametric equation of the circle, we can use the definition of cosine and sine. The definition of these trigonometric functions is the following. If we rotate a unit vector with some angle, then the rotated vector's x-coordinate will be the cosine of the angle, and the y-coordinate will be the sine of this angle. So cosine and sine together define origin-centered unit circle. If we want to have a general circle, we scale this unit circle by r, the radius of our general circle, and translate the center to the point x0, y0. In order to get a complete circle, the angle should run from 0 up to 2 pi. In many cases, we prefer to have a normalized parameter range, which means that t is in the 0-1 interval, which is possible if we multiply this normalized parameter range by 2 pi. So we have a parametric equation of the line and circle. I have to emphasize that these are not the only possibilities. There are infinitely different versions of the equation of a line and similarly to a circle. For example, if we replace t by t cubed in the parametric equation of the line, we still have the same set of points, but the dynamics of visiting these points will be different. But who cares when we are interested only in the shape? And this is true for implicit equations as well. Going back, for example, the implicit equation of the line, the roots of this equation, that is, the points that belong to the line, do not change at all if we, for example, square both sides of this equation, or substitute both sides into any monotone function. If we have a mathematical definition for a curve, as we had in case of the circle, then using the mathematical definition, we can translate it into an equation which can serve as the equation of that particular curve. So, for example, if we consider the parabola by definition is the collection of those points whose distance from a focal point f is equal to the distance from a line, where this line is defined by a unit normal m0 and position vector r0. Using vector algebra, the distance between 2 points is the absolute value of the vector, which is just the difference of these two position vectors. On the other hand, if we substitute a point into the equation of a line where the normal vector is normalized, then we get the signed distance between the point and the line in the result. In fact, the equation of the line says that a point is on the line if its distance from the line is 0. As this is a signed distance, we have to take the absolute value. Equating the distance from the focal point and the distance from the line, we obtain a constraint describing the point of the parabola, so we get the equation of the parabola. Similarly, by definition, an ellipse is the collection of those points where if we take the sum of the distances from the first focal point and from the second focal point, then we get a constant. Again, the distance between 2 points, the running point and the 2 focal points, can be obtained by calculating the difference between the 2 position vectors and obtaining the absolute value of the difference vector. The hyperbola is very similar to the ellipse. The only difference is that the difference of the 2 distances must be equal to a constant value. The cycloid is the motion of a point on our bicycle wheel when we ride on a flat terrain. The cardioid is a relative because if we are a good cyclist, we can ride not only on flat terrains but maybe on another circle. In that case, a point on the bicycle wheel would travel along a cardioid curve. Tractics is a path of a brick. When we take the brick to walk on a dog leash, finally the lemniscate, the infinity sign, is also defined by the path of a point of a mechanical structure consisting of 3 line segments. In most of the cases, we do not have a mathematical definition or a formula for a curve, what we really need. For example, if we want to draw a dolphin, we can hardly find anything in mathematical textbooks that can be interpreted as the equation or the definition of the dolphin. These curves, having no precise mathematical definition, are called free-form curves. I suppose everybody used drawing packages, so we have a concept or notion how to design such free-form curves. We use control points, which means that the user specifies points on the screen, typically with mouse clicks, and then expects the program to fit a curve onto this sequence of control points. We know that a curve is either a parametric equation or an implicit equation, so fitting means that the parameters of these equations or formulas should be obtained from the sequence of control points. We will search for parametric functions. So the points on the curve are identified as a function of parameter or time t. We don't know the algebraic form of this unknown function, but we know that the curve is generally smooth, so a reasonable choice is to say that the unknown function should be a polynomial. Assuming an unknown function to be a polynomial is really reasonable because on the one hand the computer is able to execute the elementary operations like addition and multiplication, and from these elementary operations polynomials can be built up. On the other hand, we can think of Taylor's approximation, for example, which means that an arbitrary differentiable function can be approximated by polynomials. So we are going to use polynomials where the unknowns are the degree of the polynomial and the polynomial coefficients like ai or bi or maybe a subset of polynomial coefficients for Cartesian coordinate z. So the question is how these unknown coefficients can be obtained. First of all, we want our parametric curve to follow the sequence of control points. There are 2 different levels of compromises. We call the curve as interpolation curve if the curve goes through the specified control points. If the curve just goes close to these control points, then we talk of approximation. This blue curve is an approximation curve. So this is a requirement, but even in case of interpolation, there are infinitely many solutions, that is, infinitely many different curves that go through the specified control points, but can do anything in between two consecutive control points. So to find from these infinitely many possibilities, we impose additional requirements or we set up an additional wish list. These wishes include that the curve should look natural. What is natural? A parametric function is a kind of motion. We know in physics that the second derivative of a path or a motion is proportional to the force acting upon that point-like object. In real life, forces act like deforming the object and then modifying the motion parameters. So the force is a continuous function, so must be the second derivative of the path. It means that from the point of view of natural curves, we should also expect this second order continuity, which means that if we compute the second derivative of the function, the second derivative must still be a continuous function. Our second wish is that the resulting curve should look nice, beautiful. So what is beautiful from mathematical point of view? According to our experience, we prefer curvy, spherical-like shapes. Translating this subjective wish, we can say that a curve is beautiful if it distributes the curvature uniformly. A third requirement is that the curve should be independent of the selection of the coordinate system. Of course, we will use coordinate systems because we can deal with numbers only, but this is just an artificial thing which shouldn't affect the result, although it does affect how the same result is expressed with numbers. This independence of the coordinate system will be guaranteed by the fact that we define a point of our curve as a center of mass of an appropriate mechanical system. The center of mass is an objective category. We can feel it when we touch an object. This center of mass doesn't change if we modify the coordinate system in which the object and the point is represented. There is a final wish which is called local controllability. Assume that we are almost done with our beautiful dolphin. Just the tail of the dolphin should be tuned a little. So we go there, pick a control point near the tail and modify it a little. If, as a result of this small modification on the tail, the head of the dolphin changes completely, then you can imagine that the designer would be a primary candidate for a heart attack. This is not usable. So we want a strategy where the modification of a control point near to the tail affects the shape of the curve only in a limited neighborhood and leave the curve far from the control point unaffected. So let us meet our first curve type called Lagrange interpolation curve. The definition of the curve is the following. Suppose we have control points R1, R2, etc. and we also specify the time or parameter values where the parametric curve should be exactly at the first control point, at the second control point, and so on. Based on these requirements, we are looking for a polynomial with the minimum degree that satisfies these constraints. So more formally, we are looking for polynomials, that is, polynomial coefficients, so that when the known T1 is substituted into these unknown polynomials, we get the known first control point back. When the known T2 value is substituted into the polynomials, we get the second control point back, and so on. These specific parameter values are called knot values. The first question is the degree of the polynomial. Note that we have n number of equations. In a polynomial of degree m, we have m plus 1 number of coefficients because the indexing starts at 0. The number of equations is equal to the number of unknowns if the degree of the polynomials is n-1. Having made this decision and having made the substitutions, we get a linear equation for unknown parameters ai, bi, and ci. So if we solve this linear equation, we get the polynomial, and if we have the polynomial, we can evaluate this polynomial for arbitrary parameter t. So we are done. In fact, we do not even have to solve these systems of linear equations because we can tell the result without solving them. The interpolating polynomial looks like this. We take the control points and weight the control points by weighting functions and add them up. The weighting functions are shown here. A weighting function is a ratio where both the numerator and the denominator are products. In the denominator, we take the not value of the current weighting function I and subtract all other not values from it, and these differences are multiplied. Obviously, we should skip the case when I is equal to j, because in that case the difference would be 0, so we should divide by 0. The numerator of the weighting function is quite similar to the denominator, but the not value of the weighting function is replaced by the free parameter t. Again, we skip that term where j is equal to I. Indeed, this is an n-1 degree polynomial in T. It can be shown that summing these weighting functions for all possible I values, the sum is equal to 1 for every T. So what we see here is just a center of mass formula, because dividing by the total mass can be saved if the total mass is always 1. So this formula expresses the curve at a particular parameter t as a combination of the control points where the masses are specified by these weighting functions. Let us prove that this really gives back the Lagrange interpolation scheme. So if we substitute tk into this formula, then we get rk back. First, let us examine the weighting function when t is replaced by the not value of the case control point, tk. T that shows up here and there is replaced by tk, so we have two products in the numerator and in the denominator. Let us examine two different cases. In the first case, k is assumed to be I. So if I is equal to k, we have a product in the denominator, and the numerator is the same because we assume that I is equal to k. Where the numerator is equal to the denominator, the result must be equal to 1. The other case is when k is not equal to I. In the numerator, we subtract all other tj not values from tk and multiply them together. As all possible not values are considered for one of the factors in this product, this difference will be 0, so the product itself will be 0, which means that the weighting function when k is not equal to I is equal to 0. After recognizing this, let us substitute tk into t in the definition formula for the parametric curve. So tk also shows up in the weighting function. So we have a sum where we visit all I indices. However, from these terms, all but one term is 0, because for all terms where I is different from k, we concluded that this weighting function is 0. So from this sum, only one term remains in the result when k is equal to I, so we get rk, which is just the interpolation requirement of the Lagrange interpolation scheme. Let us implement this Lagrange interpolation curve. So we have a class implemented in C++ that has two data members, the control points which are points in the three-dimensional space defined by three Cartesian coordinates. Additionally, we need to store the not values for every single control point, that is, the parameters for which the interpolated curve should be exactly at the given control point. At control point, member function builds up the curve when it gets a new control point. This new control point is added to this dynamic array control points, and we need to find a not value for this control point as well. If the dynamics is not important, so we use this scheme for the definition of the shape, not for the definition of a motion, then the not values can be determined automatically. The only important requirement is that it should define a monotone sequence, because this sequence specifies the order in which the curve will visit different control points. In this implementation, we just assign the natural numbers 0, 1, 2, 3, etc. to the subsequent not values. When the curve is designed, so we have the control points and the not values associated with the control points, we should draw it. Drawing means that for the parameter range of the curve, we should find points on the curve. So we need a function, an RT function, where the input is the parameter and the output is just a point on the curve. This is just the implementation of this formula, which says that the value of the parametric curve can be obtained by evaluating a sum where the control points should be weighted with the Lagrange weighting functions. This is going to be a sum, so the result is initialized to 0, and in a for cycle we visit the control points and add the contribution of control point I to this RT, which represents just the RT function. The control point I is just multiplied by this LIT function. The LIT function is here. We have the formula for the LIT function. So it is going to be a product, so we initialize the output value to 1. In a for cycle, we visit again all possible not values. And for a given not value, a factor from the numerator and the factor from the denominator are taken, and their ratio is multiplied to the result. Of course, we skip the case when I is equal to j, because that would lead to a 0 in the denominator, so our program would crash. When the for cycle is over, in the Li parameter we have the value of this function, so we return, and the returned value is used as a scalar for the control points as required by the Lagrange interpolation formula. Let us analyze this curve for the case when we have 4 control points. The green control points should be visited when the parameter is 0. The blue control point is visited when the t parameter is 1. The yellow is visited when the t parameter is 2. And the final red control point is visited or interpolated when the t parameter is 3. So with this, we have the 4 control points and also the 4 not values, 0, 1, 2, 3. If we have the not values, we can unambiguously specify the polynomials of the weighting functions, these LIT functions. In this graph, I depicted the 4 weighting functions. The green curve is the weighting function of the green control point, the blue is the weight for the blue control point, the yellow is the weight function of the yellow control point, and finally the red curve is the weighting for the red control point. Now let us assume that the t parameter is equal to the not value of the very first control point, so t is 0. From this figure, we can read that in this case the weight of the green control point is 1, while the weights of all other 3 control points is 0. So this is a mechanical system when all weight is concentrated in a single point, so the center of mass will also be in this green point. for t equals 0, the Lagrange interpolation curve will interpolate the first control point. Let's increase t. The contribution of the green control point decreases. The contribution of the blue control point increases. The red control point also has some positive effect, and the yellow control point has a negative effect. So it means that the blue control point will attract this curve the most intensively. The green control point and the red control point will also attract the curve, while the yellow control point will repel the curve. So in this domain, the curve will go along this path. And when t is equal to 1, the blue weight will be 1 and the weights of all other three control points will be 0. So again, the center of mass of the system will be in this blue control point for the case when t is equal to 1. And the behavior is quite similar. If we further increase t, the contribution of the yellow control point increases, the contribution of the blue control point decreases, and both the green and the red control points repel the curve a little. And when t takes 2, then all mass is concentrated in the yellow control point, so the curve will interpolate this yellow control point. If t is increased even further, then the red point will be dominant, the yellow point will lose its attractivity, the blue point repels some degree, the green point has also some effect, but when t is equal to 3, only the effect of the red control point remains, so the curve will arrive at this red control point. This is how the curve behaves when we consider the pool parameter range. It's worth making a few observations. On the one hand, these weighting functions are non-zero in the whole domain except for the discrete points of the knot values. But the red control point has some effect even close to the beginning of the curve. So this curve is not locally controllable. We can also observe that a weighting function changes its sign at knot values. When we look at the parameter range globally, a control point attracts, then repels, then attracts again, then repels again, attracts, repels, attracts, repels. This is really bad because this results in oscillation, so it is against our requirement of beautiful curves. So probably we will not be satisfied with the Lagrange interpolation curve. So let us test it and see whether it is appropriate for drawing a dolphin. Let's start at the tail. So this is the first control point, second, third, fourth. And the yellow Lagrange interpolation curve indeed interpolates these points. So far, so good. I cannot complain. Okay, let's add further control points. It's getting worse. Yeah, it's very bad. It's uncontrollable. So I stop. So this curve is really very, very far from the contour of the dolphin, and it seems uncontrollable. For example, I might fix the curve here in this range by editing the control point, and it might be fixed, but as you see, when I modify the control point here, the curve is also modified here, very far from the moved control point. So this is not locally controllable, and we cannot really do anything with this uncontrollable oscillation. So this Lagrange interpolation curve cannot be used to draw complex curves, cannot be used for dolphins. The Lagrange interpolation curve can be generalized, and we obtain the Hermite interpolation. In the Hermite interpolation, we can specify not only the control points, but also the derivatives at these control points. We call that the first derivative of the motion is the velocity vector, the second derivative is the acceleration, and so on. So in the Hermite interpolation, we may specify not only the locations at certain points of time, but also the velocities, accelerations, and so on. The Hermite interpolation approach suffers from the same problems, namely the oscillation, similarly to the Lagrange interpolation. Similarly to Lagrange interpolation, it is good when we have just a few control points, but becomes uncontrollable if we want to use too many constraints. Therefore, we discuss the Hermite interpolation only in a special case, when we have only two control points where also the velocities are prescribed. In our special case, we have pi and pi plus 1, the two control points, the velocities of the motion here, vi and vi plus 1, and we know the points of time when the motion must be here, so these knot values are ti plus 1. We are looking for a polynomial function that meets these requirements. The first question is again the degree of the polynomial. In our set of requirements, we have four constraints: the starting point, ending point, starting velocity, and ending velocity. Therefore, we need a polynomial where the number of unknown coefficients is also 4. This is the cubic polynomial. So we search the solution in the form of a cubic polynomial. Generally, a cubic polynomial looks like this. Polynomial coefficients a3, a2, a1, a0 are still unknown. As we have also requirements for the velocity vector, which is the first derivative of the motion, we also compute the time derivative of this general cubic polynomial. Now let us consider the requirements one by one. If we substitute ti into t in our general cubic polynomial, we should get pi back, the starting point of the motion. If we do the substitution, these terms are cancelled and we are left with a0. So we immediately know one coefficient from the four unknown coefficients when we consider the starting point of the motion. Doing the same for ti plus 1, that is considering the ending point, it is not so simple, but what we can say is that this expression must be equal to the prescribed ending point pi plus 1. Let us do the same for the velocities. So if we substitute ti into the derivative of the motion, which is the velocity of the motion, we should get vi back. Doing the substitution, we are left with ai, so we know even the second coefficient of the unknown polynomial. And finally, we repeat the same substitution for ti plus 1 when we need to obtain the ending velocity of the motion. So we have four unknowns, from which two are already known, and two additional unknowns with two equations which are not considered yet. So this is a quite simple linear system of equations which can be solved, and the solution is summarized here. From the starting point, ending point, starting velocity, ending velocity, and the dot values, that is the time at the beginning and at the end, we can obtain the four unknown coefficients. So the Hermite interpolation curve is fully specified. Let us return to our original concern about the uncontrollable oscillation of Lagrange and also Hermite interpolation if we have many control points. Recall that this oscillation is caused by the property of the weighting functions, which are either positive or negative and change their sign in subsequent knot intervals. This oscillation can be removed if we can guarantee somehow that there is no change of sign in the weighting functions, so a control point can only attract the curve but never repel it. Let us continue searching for the parametric form of the curve in the form of weighting the control points with weighting functions, while assuming that the sum of the weighting functions is always 1. So this formula is nothing but the center of mass of the control points when we distribute B0 weights to the control point of index 0, B1 weight in the control point of index 1, and so on. If all weights are non-negative, then the center of mass must be in the convex hull of the control points, and it also suggests that the curve will be free of unjustified oscillation which would go out of the convex hull. So our objective is to find a set of weighting functions Bi that guarantee two properties. The sum is always 1, so this formula is just the center of mass formula. And the weighting functions themselves are non-negative, so the center of mass is in the convex hull. In case of the so-called Bézier approximation, these weighting functions are the Bernstein polynomials. So what are these Bernstein polynomials? Let us take 1 and compute the nth power of 1, which is still 1. Let us express this one in a little bit more complicated form as t plus 1 minus t, and use the Newton's binomial theorem to express the nth power of this sum. According to the Newton's binomial theorem, this is equal to the following expression, where the terms of the expression are just the Bernstein polynomials. From this definition, it is easy to see that the Bernstein polynomials meet the two requirements. On the one hand, Bernstein polynomials are always non-negative if t is in the unit interval from 0 to 1, because n choose I is non-negative. If t is non-negative, then the ith power of t is also non-negative, and if t is not greater than 1, 1 minus t is also non-negative. Additionally, if we add all Bernstein polynomials for an arbitrary t, using the Newton's binomial theorem, we get the nth power of 1 back, which is 1, so the second requirement is also met. This is the implementation. In the Bézier curve, we need to store only the control points. There are no not values here. The active parameter interval of the Bézier curve is always the unit interval. The curve always starts at t equals 0 and ends at t equals 1. That cannot be changed. When the curve is built, we just add the given control point to the dynamic array of the control points. When the curve is drawn, we need this RT function that computes the point corresponding to parameter t. The general formula is here, so this is a sum. The result is initialized to 0. We visit control points one by one in a for cycle and add the contribution of control point I, and this contribution is the position vector of control point I multiplied by the weighting function Bi of t. This Bi of t is here. We know the formula, n choose I multiplied by the ith power of t multiplied by the n minus ith power of 1 minus t. So in this for cycle we compute n choose I, which is multiplied by the ith power of t and by the n minus ith power of 1 minus t. We can also analyze the behavior of this curve. Suppose again we have 4 control points. So the degree of the Bézier curve is 3 because the index starts at 0. So from 0 up to 3 we have 4 Bernstein polynomials. If we know n, the Bernstein polynomials are fully defined, so we can draw the 4 Bernstein polynomials of this case, which will describe the weight placed at the green, blue, yellow and red control points. When t is 0, we can recognize that the green control point has weight 1 and all other control points has weight 0. So the center of mass of this mechanical system will be in the green control point. The Bézier curve will interpolate its very first control point. If we increase t, then the green control point will lose control quite quickly and the blue control point will be dominant, but not fully dominant, because even when the blue weight is maximal, the green, yellow and red control points still have some effect on the curve. Note that these effects are always positive, so a control point can attract the curve only and can never repel it. As the blue control point can never have the full weight, the curve typically doesn't cross the blue control point. The curve only approximates the blue control point, but the curve doesn't go through it. If t is increased even further, the dominant control point will be the yellow one. Other control points also have their effect, so the yellow control point is also approximated. When we arrive at the end, so t is equal to 1, the total weight of 1 is concentrated in the red control point. All other contributions will be 0, so the last control point is interpolated, not only approximated as the blue and the yellow control points. So this is an approximation curve. Is it able to draw dolphins? Let's try. I start at the tail. The Bezier curve doesn't go through all the control points because it is an approximating curve. There is no oscillation, so I can be satisfied with this. But if I insert more and more control points, then because of the approximation property, the curve will be pretty far from the control points. So this yellow curve is not exactly the dolphin. I might modify the control points, but as you can see, it is almost impossible to have a quickly changing shape like the dolphin comparing to the Lagrange interpolation curve. My Lagrange interpolation curve is hyperactive. Bezier curve is too much sedated. So we need another solution. Both the Lagrange interpolation and the Bezier approximation approaches try to fit a single polynomial to the control points. Therefore, the degree of the polynomial grows with the number of control points. And sooner or later, this becomes unmanageable. In the case of Lagrange interpolation, we can see oscillations. In the case of Bezier approximation, we see a blob-like behavior which cannot handle quick changes. Maybe it's a bad idea to fit a single curve to a complicated sequence of control points. So a better idea is to use splines, which means that we do not want to fit a single high-degree polynomial to all control points at once, but consider smaller parts of the control point sequence and fit low-degree polynomials to these small parts. However, we have to guarantee somehow that when these small curved segments are connected, the connection will also be smooth. There are many different splines. I will introduce just a single one, the Cat-Mouron spline. The idea here is that we insert an Hermite curve between every two consecutive control points. The Hermite curve is defined by the start and the end, and the velocity at the start and the velocity at the end. We want these curved segments to join smoothly. This smooth join can be guaranteed at some level if subsequent curved segments share the velocity vector at their meeting point. And this is true for an arbitrary selection of the shared velocities. To step even further, we want to have at least approximately C2 continuity. That is, the continuity even the second derivative. C2 continuity is approximately guaranteed by the Cat-Mouron spline with a clever heuristics. We can use arbitrary velocity vectors that are shared by two subsequent curve segments. This velocity vector should be selected in a way that the second derivative continuity is at least approximately guaranteed. So let's see how an appropriate velocity vector can be found at a particular point. Assume that the motion is a linear uniform motion between these two control points. then the velocity of this linear motion would be the translation, which is Ri minus Ri minus 1, divided by the time needed by this motion, which is Ti minus Ti minus 1. This fraction is just the velocity of the uniform motion here. Similarly, if we had a uniform motion between control points Ri and Ri plus 1, the velocity vector of that uniform motion would be here. So a reasonable choice to say that in the smooth curve, the velocity vector at this particular point should be the average of the velocities of the two uniform motions ending and starting from here. So this is the Catmull-Rom formula for finding the velocity vector at a point, and when all velocity vectors are available, using the Hermite interpolation strategy, all these curve segments can be found. We should use a small trick at the very beginning and at the very end, because at the beginning there is no previous point and at the end there is no consecutive point. For example, here we can prescribe the velocity vector or say that motion should start in the direction of the next control point. With this, all velocity vectors are available, so we can compute the Hermite interpolation curves between any two subsequent control points. So the curve is ready. Let's see the implementation. In the Catmull-Rom object, we store the control points and also the knot values, the parameter values, where we expect the curve to be exactly in that particular control point. That control point is similar to the implementation of the Lagrange interpolation curve. The other important member function is the evaluation of the RT function to compute a point that corresponds to parameter t. First of all, we have to identify that curve segment that is valid for the given parameter t. So we have to test knot intervals for inclusion of the current t parameter. And if we find an index I for which interval ti and ti plus 1 contains t, we know that we have to use that particular curve segment. Here, we have to compute the velocity vectors at the beginning of the segment and at the end. We have the formula for that. And when the velocities are available, we can call this Hermite function. The Hermite function is here, that gets the starting point, starting velocity, the parameter at the starting point, ending velocity, and the parameter in the ending point, as well as the parameter t for which this cubic polynomial should be evaluated. The cubic polynomial has 4 coefficients which are computed according to the Hermite interpolation formula. Let's do the dolphin test. It's not bad so far. If I'm not satisfied, I can pick a control point and fine-tune it. I know that when I am fine-tuning the curve on the head of the dolphin, nothing really changes in the tail, even if I introduce brutal changes. The tail is not affected. In fact, the curve is modified only in the neighborhood of the control point. This Catmull-Rom spline is locally controllable. So we can conclude that this Catmull-Rom spline is indeed a good solution to draw complex curves. Why is it locally controllable? Let's go back to the definition of the Catmull-Rom spline. We use Hermite segments, and a single segment is defined by the starting point, ending point, starting velocity, ending velocity. For the starting velocity, we use also the previous control point, and for the ending velocity, we use also the next control point. For a line segment, only 4 control points contribute. With this, we arrived at the end of curve modeling. In the next chapter, we are going to increase the dimension and will consider surfaces in the 3-dimensional space. Until then, thanks for your attention.